Hello everyone and welcome back to a brand new episode of the Funtastic Academy with me, Ayush Prasad. In this episode, we're going to pick up where we left off last episode, discussing various sorting algorithms and their time complexity. Last time we looked at bubble sort, one of the slowest sorting algorithms in the world. But this time we look at insertion sort, a new algorithm. Does it fix the holes that bubble sort has? And does it have a better time complexity? Well, we need to ask computer Ayush to find that out. But before that, we need to answer last episode's quiz question. Who was the person who came up with the name bubble sort for that sorting algorithm? The answer is Kenneth Iverson, a famous computer programmer who invented the APL programming language. APL stands for A Programming Language. In the book about that programming language, he is generally regarded to be the first author who uses the term bubble sort. So, now that we've covered that, without further ado, let's cut to computer Ayush who will explain how insertion sort works.
This is insertion sort. Everyone say hi to insertion sort. Insertion sort works in quite an interesting way. I'll just explain how it works here before showing how the actual code works. It's again extremely simple. I based this off an optimized version that in the right programming language and optimized compressed is only 3 lines of code to sort the whole list. Here's how it works. You essentially try to make sure that at all times the first something amount of elements of the list are sorted. And then you just increase something slowly and wait until something equals the size of the list. So in this first iteration, the first iteration of this outer loop, we make sure that the first 2 elements are sorted. Then we make sure that the first 3 elements are sorted. Then we make sure the first 4. And this step is to make sure that all 5 elements are sorted. So let's see how this works under the hood. From I equals 2 to n, we should set a temporary variable to our ith element. And we set j to the position of I. Now, while j is greater than 1 and the j minus 1th element is greater than t, we set a of j to a of j minus 1 and decrement j. After that is done, we have j in the right spot and we can set a of j to what was previously a of I. I'll explain how this dark wizardry works in a second. I promise it's simple. So in the first iteration, I is 2. So I is the second element here, or rather the position of the second element. And t is actually the second element, which is the number 2. J is also equal to I. Now, this statement, all that it means is that it's pushing j backwards and backwards into the list until it finds the right place. See, when we start, we can assume that the first 1 element of the list is sorted, because a single element is always sorted. Then we just take the next element that's not sorted, which comes after the something, and finds its correct place in the part that's already sorted. This is what this while statement does. It goes backward into the part that's already sorted, trying to find where it properly is. And this just pushes everything back as it goes. So in this first iteration, when I is 2, we just swap 2 and 3. We take 2, swap it back where it's properly placed. Then in the second iteration, we put the 7 into the correct spot. But 7 already is in the correct spot, and this is where the magic happens. This while statement never executes because 7 is already in the right spot. So we don't do this inner portion. which actually adds quite a bit of time to the thing. This is different from bubble sort, where it always executed all these loops. Then we set t to 5, and we set t to 1, and we need to find 1's correct place in the list. We're swapping backward to find where 1 should be. And this is the hard part because 1 should be all the way at the back of the list. So we slowly push it backwards. The way I've drawn it is not how this optimized implementation works. It's effectively the same thing, swapping backwards, but effectively what it's actually doing is that this should be a 7, this should be a 5, and only at the end, where we know the 1 should be in the right place, do we add the 1 back. So it does the same thing, but it just a shorter lines of code. This is also a form of insertion sort. So now that we know how this algorithm works, let's analyze it. So this outer loop executes n minus 2 times. And all the stuff that gets executed n minus 2 is also a leading factor. But we also have this while loop. Now, how many times does this get executed? Well, remember this whole segment where we had to swap 1 all the way to the back? It's in the front, it needs to be in the back. And so we push it all the way down. That's the same thing that's happening here, essentially. It checks where I need to swap it for how long. Let's say the list is in exactly the wrong order. Let's say the biggest elements are in the starter list and the smallest elements are at the back. Then, well, every time we go to this loop, we'll need to do the exact same thing as we did in these last 5 steps. So this loop will be executed, well, all the times that we have. So on the first try, it will only be executed 1 time, but then it will be executed 2, then 3, and so on and so forth all the way till n. And we can again do the summation using the same Gaussian formula we did last time. This is n squared, this time plus n divided by 2 because we're adding that extra n. Now, you might think this number is bigger than the number we got from bubble sort. And this is also often squared, in fact. This overpowers the other n minus 2 stuff. And so the n squared makes this often squared, the same as bubble sort. Why is this possibly faster? Why do people actually use this algorithm, unlike bubble sort? The difference is that it self-aborts in some situations. When the 5 got swapped between the 7 and 3, and we wanted to check whether it got swapped before the 3, it didn't, right? So we aborted. We went swapping the 1. Bubble sort doesn't do that. In its current form, it always tries to push the element all the way to the magnetic list, but the largest element all the way back, the second largest all the way back, and so on and so forth. It always takes these loops. The way we've coded insertion sort, it doesn't do that. Inserting the right element into the right place in the list, and once it's done, it can stop. If it's already in the right place, like we saw in 7, it doesn't do anything. This inner loop doesn't even execute. Unlike here, where the inner loop always executes, it just has an if statement inside. So that's why insertion sort is actually practically used. In fact, if you have a really small list, insertion sort is the fastest algorithm you can use in most circumstances. There's some heavy algorithms that will give you smaller time complexity, but they have a lot more boilerplate to add, and on the real computers that adds a lot of stress. So insertion sort is a really useful algorithm, despite it being often square. And the lesson learned is that you shouldn't take these order values too seriously. You should think about how they can also work in context. Ooh, that was a deep marvel. Now back to camera, just to recap what we just learned. I think that's it.
Thanks for that, Computer Ayush. Let's do a quick recap. In today's episode, we learned about insertion sort. It's an algorithm that, as we saw in the trial run we did, fixes many of bubble sort's flaws. So you'd expect it to be much faster, but it has the same n squared time complexity. So what did we really learn in this episode? We learned that time complexity is not necessarily a good way to rate an algorithm speed, and you can always design new innovative algorithms. So, on that note, let me leave you with this quiz question regarding how insertion sort might be faster than bubble sort even if it has the same time complexity. Insertion sort might always be O of n squared, but for what special inputs is it the fastest speed O of n? Tell me the answer, and I'll see you next time on the next episode of the Funtastic Academy. Bye!